This is Geometry, Chapter 9, Section 5, in which we will study symmetry. Okay. Symmetry is one of those things that you've been talking about since elementary school. When we talk about a figure having symmetry, what we're talking about is if one of the congruence transformations maps the figure onto itself. Okay. We're talking about a rotation. If you can rotate it and get the same shape back, oriented the same way, then you have symmetry of rotation, or a line, or an axis, or a glide, or things of that sort. Okay. Now, typically, what we're really interested in are line symmetry, which is basically a reflection, rotation symmetry, plane symmetry, and axis symmetry. And we're going to look at all of those options. Okay. Reflectional symmetry, that's the term I learned, but your book uses line symmetry. That's the situation that you're most familiar with. If you have a line so that the figure folds over onto itself, then you have a line of symmetry. Okay, this is the one that you're used to the most. It's the one you've been doing the longest. So we have some pictures here, some figures, and our job is to find lines of symmetry if there are any. Okay. So we look at this first one. If I draw a line, and I'm going to get myself a dotted line, not that big. If I take and try to draw a dotted line across there, this isn't symmetric there because this point's reflection would be here. That's no good. What about, let's turn it 90 degrees. Is there symmetry here? This point's image would be like here. If we put this at the midpoint of this segment so that these two matched, these two clearly don't match, so there's no symmetry there. Come on, line, cooperate. Maybe there's diagonal line symmetry. Well, let's see. This perpendicular distance here would put that point there. No. Nope, there's no symmetry in this one. So this first one has no lines of symmetry. There aren't any. There's no symmetry involved in that one. Guess I could have kept my line out. But what about this square here? If I'm careful with my drawing, and I go right through the midpoint of it, that has symmetry. So there's one line of symmetry. There's another one going this way because it maps perfectly on that direction. So that's 2. Since it's a square, it maps perfectly that way for 3 and that way for 4. So this one has 4 lines of symmetry. Okay. What about our regular pentagon here? That certainly is a line of symmetry. That's 1. There's 2. 3. 4. And yes, even 5. That one has 5 lines of symmetry. And now the fun one, a circle. Circle has more lines of symmetry than you can count. Right? Everywhere, as long as I go through the center of the circle, I've got a line of symmetry. That one has so many lines of symmetry that it has a special symbol. Infinity lines of symmetry. You can draw it as a sideways 8. Some people actually turn their paper sideways, write an 8, and then turn their paper back to keep working. Whatever floats your boat. So that's line symmetry that you're comfortable with for the most part. Rotational symmetry, which is also called radial symmetry in some books, is something where you can rotate the figure around a certain point, typically in the center of it, and end up with the same orientation. So what we're talking about here, that point is called the center of rotation. Now I'm going to jump back over here and get my trusty square here, just to give you an idea of what we're talking about. Get rid of some of these lines. Okay. If I take this square and I rotate it 90 degrees, I have exactly the same thing I started with. Or if I rotate it 180 degrees. Okay, this thing has rotational symmetry, because no matter how I turn it, I can get back to where I started. Same thing with the circle. The circle has a lot of rotational symmetry. Okay. This pentagon has rotational symmetry, right? I can turn it, and if I was careful about it, okay, I get back where I started again and again and again. Okay. That one's harder to see because of the angle involved. This guy doesn't have rotational symmetry. I mean, even... well, maybe you could say it has 180. Okay, but that's what we're talking about, rotational. The number of times that you map back to yourself as you go through a full circle is called the order of the symmetry. So our square had an order of symmetry of 4, because it mapped on 4 times. The magnitude of symmetry is the smallest angle that you need to be able to rotate onto yourself. So in the square's case, that was 90 degrees. And there's a nice rule. The order of symmetry times the magnitude is equal to 360. Okay. Think about the pentagon that we had. There were 5 different places that it matched up. So the order of symmetry would have been 5. I can figure out the magnitude then. 360 divided by 5 gives me a 72 degree magnitude of symmetry. So I can use this formula to figure out that angle. Or if I know the angle, I can figure out the order. Okay. So let's see if we have any rotational symmetry here. Okay. We'll start with the star. So I've got a nice star here. As I rotate it, do I get the same shape back? Well, not quite. Do any of them match exactly? No. Not until I go all the way around. They don't match exactly. So this one doesn't have rotational symmetry. You would have thought it would, but it doesn't quite, because it's not a perfect... had this been a perfectly aligned star, it probably would have. Okay. Let's try the octagon out. Oh, there's a good one. That's 1, 2, 3, 4, 5, 6, 7, and now I'm back around 8. So the order of symmetry was 8. 360 divided by 8 is 45, so the magnitude of symmetry is 45 degrees. Order 8, because there were 8 times. Magnitude, 45 degrees. Okay. Let's try this one. We've got an exact copy of it. As I rotate around, hey, I hit a good match there. 1, 2. So it has an order of symmetry of 2, which means 360 divided by 2, the magnitude is 180 degrees. Okay. That's not too tough then. The hardest part is picturing it. You may need to trace the picture and then rotate it so that you can see it. Last thing we have to get through on this one deals with three-dimensional figures. So we have plane symmetry and axis symmetry. Plane symmetry is basically line symmetry for 3 dimensions. Alright. And axis symmetry is basically rotational. Okay. We have a cone here. If I draw a plane, if I cut a plane right through the middle of it, the top part of the cone here matches the bottom exactly. So this has plane symmetry for sure. Also, if I draw a line to the center, it will rotate around that line and keep the same shape. So this one has both plane and axis symmetry. Let's tangle with the football here. The football has plane symmetry because I can cut it right down, slice it from end to end, and the top half would match the bottom half. We're ignoring the stitching. Okay, ignore the laces on it. Anytime they give you, like, baseball, volleyball, anything like that, ignore the stitches, the seams, the laces, and just look at the shape itself. It also has rotational symmetry because I could draw a line through here and rotate it. Okay. This guy also will have both plane and axis. I could cut a plane vertically right through the middle. Okay. Picture a saw. If I use this as a saw blade, this is going to be really hard to see, but if I cut right down the middle of it, then it's the same on the left and the right, or the front and the back, as it were. So this has both. This one only has plane symmetry. I can cut it, again, right down the middle of the stair-step thing, whatever you want to call this. Okay. Three-dimensional ones are harder to see. Sometimes I just close my eyes, picture the thing, and see if I can find a way to slice it in half or anything of that sort. But these are the hardest ones to see. Best advice I can give you is just to visualize it. If you had questions along the way, hopefully you wrote those down. Bring them in, and we will see you in class.